Good morning. So let's begin from where we left last time. So we were looking at heat diffusion equation, and we had derived the heat diffusion equation in the Cartesian coordinate system. So I want to look at two other coordinate systems today. One is the cylindrical coordinates, and then we look at the form of the heat diffusion equation in spherical coordinates as well. Now we use cylindrical coordinates typically when you have a problem which either has heat diffusion in a solid which is of a cylindrical shape, or in problems where some kind of angular symmetry is encountered, or is quite inherent. And the way the cylindrical coordinate system, just to remind you, the way the cylindrical coordinate system works is, if we have, let's say, the Cartesian system, let's say x, y, and z coordinates, and we have some point, I don't know, maybe P in that system. So we are going to write point P in terms of new coordinates, and the new coordinates go as follows. If you drop a perpendicular from the point P on the xy plane, then where it intersects will of course be the z coordinate or the height. And if I join, say, the origin to this point where it is perpendicular, so this angle is 90 degrees there. So this distance is the radius r, and the location from the x-axis is given by the angle phi, which is the azimuthal angle. So the coordinate for point P will then be r, phi, and z, or z. So knowing this, we can describe every point in a, I mean, it need not be a Cartesian system. Every point can also be described by cylindrical coordinates. So in a cylindrical system, instead of going through very detailed derivation, what I'm going to give is a brief idea of how the cylindrical coordinate or how the equation is developed in cylindrical coordinates, without going again, as I'm saying, in a detailed derivation. So say we have the origin somewhere, okay, and I take a differential element. Remember, there as well we took a differential element which had a volume of dx, dy, dz. So we'll take a differential element at some distance r, let's say, from the origin. So I'm going to say that this distance is r. Okay. So the equal to sign that it appears, it actually is supposed to indicate that it's a long way, in a long way, distance away. It need not be so nearby, but it's applicable for any system, for any distances. And then we have a differential element which would have maybe the following dimensions. So at a distance r, we'll have three coordinates to describe this differential element. Okay, one is, since it's at a distance r, I can say that the distance along in the differential element, the distance along the radial direction, which is this distance, is dr. So that is the thickness of the differential volume. The height, or the distance along this direction, is dz. And then interestingly, the distance along the curved section, which is where the angle phi comes in, that will be r d phi. So I can say this curvilinear section has a length of r d phi. So in this differential volume now, we can apply energy conservation again. So for instance, at the back face, which is in the radial direction, there would be some qr that would be coming in, and what would be leaving here is q r plus dr, normal to that face. And then we have q phi coming in, and what is leaving is q phi plus d phi. And then at the bottom face I can say we have q z coming in, and then what is leaving from the top face would be q z plus dz. So we'll have to apply energy conservation on this differential control volume to be able to derive the conservation law. So instead of deriving that, let me just say that a few things that you should know about this differential control volume is that the volume of this differential CV will be R. So now you can imagine that this is a small element. So I can approximate that to be a cuboid. So the volume will be R d phi, which is one dimension, into dr into dz. So that is the volume on which conservation has to be applied. And I can write the flux vector. So q double dash, which could be written as qr, let's say er cap plus q phi, sorry, double dash, e phi cap plus q double dash z ez cap, where these e vectors are actually the unit vectors along each of these directions. So we can write this as, so minus k. Remember now that this flux is given by Fourier's law, which is minus k gradient of t. But now the gradient definition changes because we are not in a Cartesian system. So we will have minus k times dt dr er cap plus 1 by r dt d phi e phi cap plus dt dz ez cap. So that would be the definition of the flux vector. And then of course I can say q double dash r is minus k dt dr, q double dash phi is minus k by r dt d phi, and q double dash z is minus k dt dz. So if we begin with this definition and we apply conservation equation, what we will finally get, okay, which is not something I'm deriving here, what you should finally see is 1 by r, and we don't need not derive this for the purpose of this course. You can take it for granted. I mean, there's nothing, this is not something that I will ever ask, okay, to be proved. Yes, this is for cylindrical coordinates. I think you joined a little late. So this is for cylindrical coordinates. So 1 by r uh, d by dr of r k dt dr plus 1 by r square d by d phi of k dt d phi plus d by dz of k dt dz plus q dot will be again rho cp dt dt. Okay. Most problems that I would we will be doing in this course will actually be pertaining to variation along the radial direction. So we should be or what you should notice is the form of this equation here in the conservation law, or the first term, okay, which has a 1 by r d dr of r k dt dr. So please remember this, and I'll show you. I'll say a word about this after I've covered the next set of coordinate system. There's a trick that you should know when you are trying to do these problems on the fly. You know, when you don't have the time to look at the book and you want to quickly get a solution. The second system is on spherical coordinates. And the spherical coordinates can again be described using the same method of relating them to Cartesian coordinates. So we can write, say, x, y, z is again the system in in a Cartesian plane, and then I have some point P which I want to describe in terms of spherical coordinates. So spherical coordinates will mean that this will be r phi theta. We'll use three coordinates again, but of a different type to describe this location of this point. So the distance of this point P from the origin is the distance r. So that is quite clear. Okay, that is one coordinate defined. If I put the projection of this point on the xy plane, Okay, so wherever it hits that xy plane, and then if I join this with the origin, then that angle again from the x-axis is the azimuthal angle phi. Okay, so this is again a perpendicular, and then the angle of the line OP from the z axis. So I would say this angle is what is called as a theta, which is the polar angle or the zenith angle. So some books call it polar angle, some will also call it the zenith angle. And phi I said is the azimuthal angle. Interestingly, you should know what would be the range of these variables. For instance, xy in the xy plane, xyz plane, or in the xyz system, all coordinates can go from minus infinity to plus infinity. The same is not the case when you move to cylindrical and spherical coordinates. For instance, the spherical coordinates, r is always a positive number, so it can go from 0 to infinity. Phi is essentially because it's a projection on the xy plane, so phi can actually take all values from 0 to 2 pi. So you have phi between 0 and 2 pi, so that it can cover the entire plane or points on that plane. And theta is actually can only go from 0, because 0 would be measured from positive z axis, to go to all points within the negative z axis. You will go from 0 to pi. So theta would be something like this, 0 to pi, so that you cover. Now if you think of these numbers, I mean, if you think of these coordinates, you can actually cover all points in the Cartesian system using just these three combinations. Okay, now what about the differential element? So the differential element here is slightly more complicated because it's in a spherical shell. You know, you can think of it this way, that you have a sphere and you take an element or a shell of thickness dr, and then in that dr you are going to cut a small, maybe, a differential volume. So the sketch is a slightly more complicated, so I'm not going to try and perfect it here. I will just draw what my, what I feel works for me. You may actually be able to draw it better. So we'll have a shell or an element which would be something like that. In that differential, of course I'm blowing up the small element. So the different coordinates on this shell would be, so this anyway is at some distance r. Okay, so I'm not worried about that right now. So again, let me forget about that. This is at a distance r from the origin. So this side in the radial direction has a thickness of dr. If you can imagine now that if it's at a distance r, so a differential element will actually be in an increment of d theta. So this side is actually r d theta. Oh, sorry, d theta, not d phi. D theta. So that would be one side of the cuboid. And the third dimension is slightly more complicated, but it can be easily understood that the third dimension or the third length, let me take, yeah, this length here that I'm not marked yet, okay, which I hope you can see with my pointer. So this length can actually be obtained because by considering that this distance r is to the point P. So if you look at the projection of this point P on this xy plane, then this distance here is actually r sine theta. So we are going to have an r sine theta taking a, r sine theta being the radius for a differential element. So r sine theta times d phi should then become the r sine theta d phi should become the dimension in that, or should become the length in that of that element in that direction. Okay, so it's r sine theta, so projection into an incremental change in that direction. R sine theta d phi is the arc length along that direction. So this volume of the CV now, of this differential CV, will be now multiplication of all these three. So we'll get r square sine theta d theta d phi dr. So in fact, if some of you, I don't know whether in your high school or somewhere, if you derived the volume of a sphere, Actually, this is where you can integrate this differential CV over all r, r from, let's say, 0 to r naught. If r naught is the radius of the shell of the sphere, theta basically from 0 to pi, and as I said, d phi is from 0 to 2 pi. You can actually get the volume of the sphere, and that's how you can verify that this element is the way it is supposed to be. So what about flux now in the spherical system? So again, flux is minus k gradient t, except the definition of gradients will again change now. So we'll have minus k dt dr er cap plus 1 by r sine theta uh, dt d phi e phi cap plus 1 by r, because one side is r d theta, yeah. So 1 by r dt d theta e theta cap is the uh, expression, or is the way of we can write flux in this direction. Okay, so then we can decompose the flux into the three coordinates q double dash r, q double dash theta, and q double dash phi. And finally, when you apply energy balance or you apply conservation of energy to obtain the heat diffusion equation, what you will get is heat diffusion equation. The heat diffusion equation will actually come out to be 1 by r square d by dr k r square dt dr plus 1 by r square sine square theta d by d phi d phi of k dt d phi plus 1 by r square sine theta d by d theta of k sine theta dt d theta plus q dot will be rho cp dt dt. So this equation will be slightly more complicated, and I'm sure you have seen some of these counterparts when you looked at when you were doing fluid mechanics, because uh, the the diffusion, I mean the three terms that I have on the left hand side, which are the differentials, they actually appear very similarly in the Navier-Stokes on the right hand side. So in the Navier-Stokes, typically on the right hand side, you have these viscous dissipation terms. So they will also have the same behavior. Okay, it's basically the Laplacian that we're writing, the Laplacian operator del square. So that will come out to be the same way in that you see in fluid mechanics, and the same thing is being carried forward in heat transfer now. So these are two more systems that we will be tackling. And so what I was saying earlier is that if you remember now, and this is just something for you to you know remember, if you want to not be worried about looking at the book every now and often when a problem of this kind appears to comes to you. If you remember, the first term in the Cartesian system was like k d by dx of k dt dx. In cylindrical, it became 1 by r d by dr of k r dt dr, and in spherical it has become 1 by r square d by dr of k r square dt dr. And this is basically what this will be the variation that we will be more interested in this course. So the way to remember, I mean, if you want to do it this way, the way to remember is that as you go higher in coordinate systems, so as you go from Cartesian to cylindrical to spherical, you basically can imagine that the general form for remembering is 1 by r n d by d, let's say, r of k r n dt dr, where n is 0 if it's a Cartesian system, n is 1 if it's cylindrical, and n is 2 if it's spherical. Okay, so that would be the first term. The second and third terms are slightly more complicated, which you need not remember. But as I'm saying, for this course, we will never go into those dimensions. We will actually assume that properties are not changing along the angular directions. But we will most likely, we will more, more problems that we do will be of property, or of temperature variations along radial direction, or let's say along one axis, maybe x axis. So then it becomes easier to to have this handy, instead of trying to look up what was the dependence in the Laplacian operator. So anyway, so just as a thought, I thought, I was thinking that maybe I'll share with you that this could be one way of remembering these dependencies. Now, how do we, so we have defined these differential equations. The question now comes in, how do we solve these equations, and then what is required to solve these equations? So of course, these are equations, and these are differential equations which require detailed mathematical procedures. We won't go into such great detail. We will only consider some special cases in this course. But then we also need to understand that a differential equation in itself gives you a general solution. The solution becomes a characteristic of the problem by the nature of the boundary conditions, and the initial condition. So we need to define for each problem a few, let's say, boundary conditions. And by boundary conditions, I also mean initial condition, because that's also a boundary condition in time. So we need one initial condition to solve these equations, because the problem is first order in time. And we will need two boundary conditions in space along each coordinate direction along which a dependence is taken. I should say along each coordinate direction. Okay. Now, what are the different forms of boundary conditions that we will see? Initial condition is easy. Typically, initial condition is that you have a system at some initial temperature, and then you impose these boundary conditions. So, how does the system respond to these boundary conditions, or this initial condition? So that is quite easy. Okay, but the boundary conditions are of different types in heat transfer, and I've covered some in the earlier lecture. But let me now very explicitly say what these boundary conditions will be. So the first type of boundary condition that you will see in our treatment of this course would be of a Dirichlet type. A Dirichlet type boundary condition is one in which you have a fixed value of the variable. So let's say in this case fixed temperature, because we are dealing with temperature as a dependent variable. So say, let's say we have a solid which has some properties, and then at some location x0, which is, let's say this is x0 here for me, I have imposed a temperature Ts. Okay, there is some external means by which I'm maintaining this temperature Ts. So the Dirichlet type boundary condition would say that temperature T at x0 for all time t is Ts, which is the easiest form that you would have also seen in fluid mechanics. Okay, so you can, based on the temperature Ts, you can actually get some dependence or some temperature variation in the problem. So we can get Tx comma T, let's say. The second boundary condition that we will use is a Neumann boundary condition, a Neumann type boundary condition. So Neumann type boundary condition is one in which you are given a gradient of the dependent variable. So gradient would mean that, let's say again I go back to the same sketch of that solid. So what we are given now is that let's say the flux on the surface is given. Okay, the value of the flux is given, which basically means that this flux will now dictate the slope of my solution from x equal to 0. So maybe the solution would have a slope of a certain type. So this is a slope line. So the slope is given at x equal to 0, which means, in a sense, what we are given is minus k dt dx at x equal to 0 in the solid is given as the flux value. So we may get a solution of temperature which would have maybe the same slope at x0, but then it goes. So this is, let's say, tx comma t. So that would be the Neumann type. There is a special case in the Neumann type condition that in case the flux is 0 at that surface, which is the case that, let's say, when uh, if q double dash s is 0, which is the case when we talk about an insulated boundary condition or an insulated surface. We will say that the surface is insulated because there's no heat going through that surface. In which case, we can then say dt dx on that surface is 0. So what happens now, that if dt dx is 0, that means that surface will have a 0 slope at that point. So I can say maybe for this case, the surface temperature distribution might be like that, with a 0 slope. This is 0 slope condition. So this might be the tx comma t when flux is 0.
Sir, right now we are discussing only the case when this conduction is one dimensional, right?
Yes, I'm saying, so I'm giving you a flavor of boundary conditions in one dimension only, but these can also be applied in the other directions.
Okay, sir.
Okay. So I've taken x to be sort of like a dummy variable for now. X could be, x that need not be x, it could be y, or it could even be z.
Okay,
Okay.
sir.
Yeah. So the slope will be 0. Of course, whether the function temperature variation will be going downwards, because there's another solution. I mean, somebody might be thinking that, why did I draw it this way? The other solution could be that we could have a function which temperature function which could be like this, because that also has 0 slope at x0. So whether it goes up or down depends on whether heat is going, which way the heat is traveling. Okay, whether if the other end, maybe this is just the close to the boundary on one side, if the other end is at a higher temperature, then the green curve is what you should expect. But if the other end is where heat is being removed from the system, from this maybe solid, then the temperature will be going down, and so you should see temperature going, the slope coming in that fashion. So there is a I mean, as long as we are clear about this, I hope that it should not be misconstrued that it always goes down. It does not always go down. It just depends on the slope. In fact, the slope for the constant flux case that I've drawn also depends on whether the flux is coming in or whether the flux is going out, because you may actually be cooling the surface. You may have a ambient fluid, or you may be pulling heat from it from through some means. So this is the Neumann type. The third boundary condition would be a mixed. Some, actually, I don't want to say this, but some books call it as a Robin type. I don't like I don't know why. Who was Robin? Who's attribute? Who is given credit for this boundary condition? Because this is not. I've never seen it. So anyway, I just call it mixed type. So mixed type basically would mean that, now let me do it pictorially instead of doing with an equation. So let's say we have this block with some coordinate system x. Okay, and if I had a cooling fluid or a fluid surrounding this block, which has a heat transfer coefficient h and temperature T infinity, and let's say we are this fluid comes in contact with the surface, okay, at x equal to 0. So then we have to have energy balance at this surface. Remember, I did that small exercise where I said at the surface is 0 thickness volume, so you can actually apply conservation of flux itself. So what do we do here? Okay, so typically I don't care about whether the surface is at a higher temperature or a lower temperature than the fluid. I do it purely by following a certain convention, and the convention goes like this. that I will attribute the heat transfer in the positive x direction to be, to be positive. So flux in the positive x direction is positive, flux in the negative x direction is negative. What it means is that irrespective of whether T infinity is more than, let's say, the surface temperature, let's say the surface temperature happens to be T0 comma T, which I don't know. Okay, this is an unknown so far, because this boundary condition does not specify the surface temperature. So what I would do is I would say that I would assume that the fluid is losing heat or is giving away heat to the surface, and the surface is conducting that heat into the bulk. So the benefit of doing that is that I can now say that Q double dash convection is coming into the surface at this in this diagram, and then Q double dash conduction is going away. So it means I can say H T infinity minus T of the surface, which is T0 comma T, which means surface temperature at x equal to 0. This should be equal to minus K dt dx at x equal to 0. So that would be the energy conservation at the surface. So H T infinity minus T means it's inherently assuming that temperature T infinity is more than the surface temperature, which need not be. It is, that's not a problem. But it's saying that this amount of heat is given to the solid, and then a solid takes it away into the bulk. Okay, so remember, it's into the surface, and then a surface conducting it into the solid. So that sign convention is very important, and this is where most of times, students actually mess up, and the solution comes out to be entirely wrong. So remember, ensure that, because as I was saying, flux is a vector. Please ensure that you've taken the right direction, and by convention, and I'm saying, follow a certain convention. If you stick to the convention, you will not make a mistake in these kinds of cases. Is this clear so far? Okay, so let's begin with the first formal analysis of conduction heat transfer, and we will be tackling one-dimensional, one-dimensional steady-state heat conduction. Okay,
Sir,
yeah.
sir, I was wondering, like, for example, if we have a cuboidal body, right,
Hmm.
and it's four of its adjacent walls, like the side walls are all insulated, so that there is no heat exchange, and the bodies, the other two ends which are not insulated, have different temperature. So can we safely directly assume that the heat transfer, like if we wish to find that path which the heat is flowing through,
Flowing.
it would be a straight line?
Yes, at steady state, not in the initial transient phase. Okay,
So why
at
not in the
steady
transit?
state, because in the transient phase, what happens is, when you have, let's say, think of it this way: you have a solid block. Okay, you have a solid block, and I can say that the other, maybe the back and front are insulated, and the top and bottom are also insulated, and suddenly you create a temperature difference across the cuboid. So what would happen is, heat would not always in the transient phase, because there is heat flow even in the other dimensions. So there would be, because those, it is not that the transfer will happen across only one layer. It has to happen across the entire layers. So there would be some diffusion of heat even in other directions. At steady state, we are so far away from this initial condition that all such perpendicular surfaces will actually be at the same temperature, but not before that.
So in the transient, say it would be like, for example, if we are trying to analyze it at a point, then it would act as a center of a sphere through which all the heat is radiating to the next part, something of that.
Center of a, what did you say? Center of a,
Like when we did
oh,
that in
of a
sound,
sphere. Did you
like,
say of a sphere?
yes, sir, sphere.
No, why did you say center of a sphere? No, it's not radiating heat. I mean, that is the
No,
so
like for
conduction.
example, like sir, for example, we were doing in sound when the sound is traveling,
Right.
it forms a particular layer. Then particle then acts again as a source of the sound, and then it creates new circular lines like that.
No, so
For example, if we go to a point, then at that point the heat is being transferred to the next points. But if we try to make a boundary layer of that heat transfer, then it would form like a hemisphere or something.
boundary layer in the case of sound.
uh,
See,
I don't know. I don't
no,
remember the
see,
name of that effect.
sound. No, I'll tell you. I'll tell you. There are certain common features between propagation of information by sound waves and also diffusion, because both work on random molecular phenomena. So sound also travels because you are actually, we are creating a pressure wave, which and pressure waves basically travel because you have these molecules which are actually going to bombard. So if I send out a signal, it bombards the next molecule, and then so that information passes on, but it happens in a random fashion. It does not happen in a in a unidirectional manner. Diffusion is also the same way, that if a surface is heated, then that information will go in an all random way, and it's a if you can think of it this way, it's a Brownian motion type of problem. It goes all possible ways, but then eventually the information reaches to the other end. Okay, that is the
Okay.
whole process of diffusion. So there is some commonality between sound propagation and heat diffusion, but of course then I would not go as far as saying that they are the same mechanisms. Okay, but yeah, it is what I'm trying to tell you in this case is that when you have this three-dimensional structure, uh, it is three-dimensional effects are only are there as long as you have exhausted all possible variations in other directions. So when you just start on the heat transfer when you give on maybe the whole surface is at the whole body is at same temperature, suddenly you switch on a different temperature on one end. So heat will conduct it. This information will be taken in by hotter, by molecules that come in contact with the hotter surface, but they will go in all possible directions. They won't necessarily go only along one direction. They don't straight away see that is the side where I can go out, or when the information can be sent out. So they go in all directions, except when the temperature of the whole thing rises, then they know that this is only one preferential way in which heat can travel. So I'm saying that first information has to go in all directions so that everything comes up, and then you can see that slope of this heat information or heat propagation is only along one direction. That happens fairly far away from the initial state. So that's why I said it's steady state. Okay, steady state does not mean, I mean, steady state just basically means that the time scale is much larger for than as compared to the rate at which information propagates in a medium. So in this case, information will propagate, let's say the length was L and thermal diffusivity is alpha, then the information will propagate at a time scale of L square by alpha, and we'll do that later. I'm bringing this very early on, but it would travel at L square by alpha. But if we go 100 times, 1,000 times of this time scale, then you would start reaching a condition where you can say that a steady state is nearly there.
Okay, sir.
Okay, but again, this is premature information. I don't know how much of you will be able to understand this until I actually get to the topic and we work out a few cases.
Okay,
Okay,
sir.
so yeah, so we'll start with this one-dimensional steady-state heat conduction. So we call it one dimensional because we will only consider variations along one coordinate system, along one coordinate direction rather. So preferably we will deal with x, but I will also do a few cases where the variation is along radial direction, so r. And I'm talking about steady state because we will talk about solutions which are independent of time. Okay, so they will not change with time, and so that's why we are saying they are steady state solutions. Now, though this analysis may appear very restrictive, and we may question why are we even doing this, because where steady state is a concept that is it is just a notional concept. You never reach steady state in any system because every system is responding to change in conditions. But this analysis of steady state heat transfer is fairly accurate. It gives you, certain on, if you are doing some calculations without going into detailed, simulations or measurements, this gives you some fairly good estimates of what must be going on in a system. So this is for engineering analysis. This is actually one of those very important scenarios which we cover, and which also is very informative and also helps us build some physical intuition. That is the most important. So we'll start with the case of one-dimensional heat conduction in a plane wall. And the plane wall problem that I would pose is something like this. So say we have a slab of a solid. So let's say that there are two surfaces A and B. The slab in the other dimensions is fairly, there are no variations along the other directions. So there is only variation along X. This is the X thing, right? So this is X, let's say 0, and XL. Maybe the slab has a thickness of L. Okay. We're dealing with steady state, so I'm not concerned about what was the initial state of the slab. We are far away from it. We have forgotten about there's no history now at steady state. Say the left end is exposed to a fluid which has a heat transfer coefficient H1 and temperature T infinity 1. So that is on one end, and say on the other end we have a fluid which has heat transfer coefficient H2 and temperature T infinity 2. The fluids may be the same, may not be the same. It doesn't matter. Actually, the analysis is quite general, so it need not be the same either. So what we are keen on quantifying is the rate at which heat transfer happens through the slab. Or the question is that given these, by the way, let me also define that the slab has some thermal conductivity K, let's say. So the question is that given the dimension of the slab, maybe the cross section area is also given. Given the dimension of the slab, the properties of the fluids on the two sides, so H1 T infinity 1 is known, H2 T infinity is known, the thickness of the slab is given. What is the rate of heat transfer through the slab? That is what we want to calculate, or we want to write. And for this analysis, I'm assuming that there is no heat generation. So Q dot is 0. We're not concerned about heat generation yet. Okay. So at steady state, I know the temperature can only be a function of X now. There is no time dependence, and there is no dependence along Y and Z directions, because as I said, they are either very large, so there are no variations along that direction. Okay. Or the system is steady state. There's only one significant dimension, the smallest dimension, so only heat conduction happens along that dimension. Okay. So what do we expect now physically? Let me explain what would happen. So what we expect is, in this case, if I say that T infinity 1, let's say, is more than T infinity 2. So the left hand side fluid is, let's say, at a higher temperature as compared to the right hand side fluid. What we expect is that there would be convection heat transfer from the fluid to the solid slab at surface A. There would be conduction through the slab from surface A to B, and then there would be convection heat transfer again from surface B to the neighboring fluid. So whatever analysis we undertake, we need to account for all these three mechanisms to be able to quantify the rate of heat transfer. So we start with the differential form of the diffusion equation. So let's write that. So we have d by dx of k dt dx plus d by dy of k dt dy plus d by dz of k dt dz plus q dot is rho cp dt dt. That was a heat diffusion equation. Now I can say that because we are at steady state, this term is 0. There is no heat generation. This is also 0. There are no variations along y and z directions. So these terms are also 0. So what we are left with is d by, oh sorry, I should now write, because temperature is only a function of x, so there is no point of writing a partial derivative. I can say d by dx of k dt dx is 0. So that is the equation that we want to solve. Now recall that in Fourier's law, heat flux q double dash x is given as minus k dt dx. So what it means is this equation is essentially saying that the heat flux dq double dash x dx is 0, which means heat flux must be independent of the spatial location. So it's the same flux at each location that we are going to work out. We don't know the value yet, but it's going to be constant. But we'll use this concept very soon. Okay. Now say, since we are saying in this problem, let's say k is constant. Say k is a constant number, which would mean that because flux is constant and flux is given as k dt dx, I can say that the temperature variation would be some would be a linear function of space. That's just by integrating the equation, the governing equation. So we need to find these constants c1 and c2 using boundary conditions. So I will do a simple case and then I will basically generalize the method. The simple case is that, or my argument is that, if the problem is at steady state, or if the system is this whole scenario is in steady state, then the temperatures at these surfaces, let's say A and B, let's say T surface at temperature at surface A as TA, and let's say temperature at surface B is TB, these temperatures T and TB will actually be constant. They will not be changing with time because this is a steady state solution. So I can actually apply boundary conditions in terms of T and TB, even though I don't know T and TB yet. That is also something that I need to determine. So I can apply boundary conditions in the following way. I can say T at x equal to 0 would be TA, which would become, this is C2, and T at, let's say, x equal to L is TB, which becomes C1L plus TA. So C1 is TB minus TA by L, even though T and TB are not known yet, and we'll determine them very soon. So clearly the temperature variation T of x is TB minus TA by L into x plus TA. So that is the linear temperature variation that we should expect in this lab. Most importantly, you should notice that this temperature variation at steady state does not depend on the thermal conductivity, and it should not actually. Okay, think about this. It does not depend on thermal conductivity because K only dictates the rate at which heat conducts. It would not dictate. So it would dictate, whether a specific system will reach steady state, earlier than something else. But the steady state solution will be the same. So this has great implications for in terms of generalization to any geometry or any material. What is the rate of heat transfer now? So we can write Qx, rate of heat transfer. This will be minus K A dt dx, right? And this becomes then minus Ka Tb minus Ta by L. And as I was saying, it depends on how you define how you look at this problem. I'm going to say that because T infinity 1 is more than T infinity 2, clearly Ta will be more than Tb. So this should be written as Ka Ta minus Tb by L, and so it's greater than 0, and so heat must be flowing from left to right. If T infinity 1 was less than T infinity 2, you will still have it as minus Ka Tb minus Ta by L, but that just means that the heat transfer is taking place from right to left, and that's still is perfectly fine. Okay, so that is the rate of heat transfer. Now let me get to addressing the point about how do we determine Ta and Tb. Okay, and I'll show you two ways of doing this. One is a longer way, which I will not prove, but I will leave you to work out. I will just give you the first few steps, but then I'll show you the second way, which is what is the most commonly used method in heat conduction um, analysis in 1D, in one dimensional cases. So let me look at the first method. Okay, to determine T and B. So we are trying to look at, or we're looking at determining Ta and Tb. So the longer way, actually it's not long. If somebody is not aware of some mathematical tricks, it can actually be done in one step, but I will just say it as a longer way. In case some of you try and use the more brute force approach, which is really long. If you figure out the trick, then it just takes hardly 10 seconds to do this. So the longer way will be that I will apply flux boundary conditions at the two surfaces. So I should say apply flux boundary conditions at surfaces A and B. So let me look at surface A first. Okay. So what is going on at surface A? At surface A, we have heat transfer by convection being carried away by in the form of conduction. So I should apply, when I apply a boundary condition at A, I will write very similar to the way I had defined the mixed boundary condition. I can say H1 T infinity 1 minus, let's say, TA. Remember, this is the surface temperature. The Newton's law of cooling requires you to define the surface temperature. It does not require anything else. So surface temperature of the solid. So H1 T infinity 1 minus TA, and for grins and chuckles, let me keep the area there. So this should be equal to the heat carried by conduction. So minus Ka dt dx at x equal to 0. It's a different thing that at x equal to 0 or at x equal to L, the flux dt dx is the same. So we'll get Ka Ta minus Tb by L. Okay, so let me just say this is equation 1. So this is first equation in Ta and Tb in terms of other variables that we know. The same thing I can do at surface B. So now at surface B, the modes are going to reverse. We have conduction flux coming in, but leaving as convection. Okay, so what I would say is minus Ka dt dx at x equal to L, which is still the same expression, Ta minus Tb by L. Now this is being carried away by convection. So what should I write? Okay, somebody has posed a question, or how are we getting A? Because that is, see, it is, you think of it this way, that it is area into the plane of the paper, and we are saying that area is going to be finite. It's going to be a solid system, right? So we are not. It's the area is there, except we are assuming there are variations along that in that direction. So the area is actually the YZ plane, but we are saying along Y and Z there are no temperature variations. Okay, that is the assumption that we're making with 1D conduction. Okay, so what should this be equal to now? Anybody, can somebody guess what should I write on the right hand side?
So H2A into TB minus T infinity 2.
Okay, good. So this should be H2A. Now we are saying this should be heat transfer to the fluid. So this should become TB minus T infinity 2. That's right. It should not be T infinity 2 minus TB. Because that would mean that heat is being given to the surface. This is heat taken away from the surface. Okay, so this is equation, let's say 2. And now I can write, so I have basically two equations and two variables. So theoretically, I should be able to solve for Ta and Tb, and then plug the values of Ta and Tb in terms of other variables into this linear temperature profile, and we will be done. Except before I ask you to do this on your own, in your leisure time, let me also say a few things. So one thing you should notice is that the conductive flux is the same in both, or the conductive heat transfer is the same in both the two equations. So I can actually rearrange this equation in a certain way. I can write this as, and watch what I'm doing carefully. T infinity 1 minus Ta by 1 by h1a should be equal to Ta minus Tb by L by Ka, and that is Tb minus T infinity 2 by 1 by h2a. So the two equations can be combined into this one common, in this one common equality. And then it actually, this is basically the trick that you can use to solve this equation very quickly, because what I can now do is, because these three are equal, I can say this is equal to some constant, let's say c. So T infinity 1 minus Ta is c by h1a, Ta minus Tb is c L by Ka, and Tb minus T infinity 2 is c by h2a. So if I add the three equations, Ta and Tb basically will eliminate, and we'll see what I'm going to do now. So I'm going to use that concept very soon. Anyway, so this is one way of doing it. Okay. Now let me look at the shorter way. The shorter way uses your understanding of Ohm's law. Okay, and it works only. This is a disclaimer here. It works only if Q dot, the heat generation term, is zero. It won't work otherwise. And the method is what is called as the electrical circuit analogy. And it follows from this last equation that I've written here. It is just an extension of this equation. Okay. The way this method works is, if you notice what I've written as in the equality there, this is actually the heat transfer rate. Qx is T infinity 1 minus Ta by 1 by h1a, which was a heat transfer rate in terms of convection. That is the same as conduction heat transfer, which is Ta minus Tb by L by Ka, which is again the same as Tb minus T infinity 2 by 1 by h2a. So in Ohm's law, if you remember, we write that the current, okay, this is Ohm's law. Current is some potential difference divided by resistance. Okay, so here we are going to use the same analogy, that Qx is actually what I can call as the heat current. Sorry, it's the heat current. T infinity 1 minus Ta is sort of like a potential difference. It's a potential for the flow of this current. So this is sort of like the driving potential difference for the flow of current. So clearly, if left hand side has a current and right hand side has some kind of a potential difference, the denominator should be some resistance to transfer of heat. So we call it as thermal resistance. So what it means is, we are now saying heat current is equal to some driving potential difference by thermal resistance. So clearly, what I can anticipate now is that 1 by h1a is a resistance to convection. It is a thermal resistance to convection. L by Ka is a thermal resistance to conduction, and 1 by H2A is another thermal resistance for convection. Okay, so you can now think of the problem in this way. So I'll draw a circuit now. So we have, on one side of the circuit, we have the driving potential, which is T infinity 1. That is a potential at this one end. This potential, which is, and through which a current of Qx is passing, it goes through a convective resistance, and I'm going to say R convective T comma 1 because it is on one fluid. Then it comes to a potential of TA, which is right here, TA. Okay, TA is here. Then this passes through a conduction resistance. So R conduction, let's say T. T just to denote its thermal resistance, not that it is time dependent. Then it comes to potential of TB. And then we have a convection resistance again, convection T2, and then it reaches a potential of T infinity 2. And all through the same current QX is passing through this network or through this circuit. So what do we now see? We see that the total resistance, because these are now in series, right? Because the same current is passing through a bunch of resistances. So these are actually in series. So I can say the total resistance in this system, R total, should be the sum of these resistances. So R convection, let's say T1 plus R conduction T plus R convection T2. So that should be the total resistance to the flow of this current. And what is the total potential difference? The total potential difference will be T infinity 1 minus T infinity 2. So we can say that the heat current QX would be the total potential difference by the total resistance. So what is the total potential difference? That is T infinity 1 minus T infinity 2 by total resistance, which I'm saying is R total, and that would come out to be R total would be 1 by H1A plus L by Ka plus 1 by H2A. So this becomes the heat current in this one dimensional problem. So this amount of heat is flowing through at steady state in this scenario where you have two fluids surrounding a slab which has some thickness L and conductivity K. Okay, is this clear? This is an important concept because I'm going a little slow on this. I hope this is clear.
Sir, in this, the heat current, like for example, when we are making this circuit, we are also assuming that this heat current is uh, passing through the mediums also, the mediums in the surrounding. But like, is it the actual case? Because basically the heat is just directly okay. The transference is also considered as the heat current, the convection.
What is considered as a heat current? Can you say that again?
The convection process that is occurring, that is
Huh.
also like the heat transfer during that also is the heat current, right?
Yes,
Like we
yes,
are
because
that.
it's going somewhere, right? If you apply energy conservation, if
Hmm,
there is heat conduction in the solid, that heat has to go somewhere. That energy has to be conserved, right?
hmm.
So that heat that comes out is either taken away by the fluid on the right side, or that is also being given by the fluid on the left side. Otherwise, if that was not the case, you know what will happen? You will have heat, you will have thermal energy getting accumulated at a point. So at that point, temperature will increase,
Okay.
right? That is the conservation law that we wrote, right? E dot in minus E dot out plus E dot generation is E dot storage. So if even if E dot G is 0, if in and out are not equal, you will have storage. Okay.
Okay.
Yeah.
So, sir, is this relation only valid for steady states?
That is a very good question. So what do you think? Yeah.
Sir, uh,
So what do you think when we did this whole thing? What is it that we assumed because of which we got this equation?
Del T by del T is equal to 0.
Hmm. We started from there itself, because if it was not steady state, because then the temperature can change locally. See, TA and TB can also change. Do you see this?
Yes, sir.
So temperatures can change. So this is actually at steady state. At steady state, this is the amount of current you can pass through, but not in the intermediate time, because in the intermediate times temperatures locally can change. Think about this.
So in that case, if we look at any cross section, then
Hmm.
heat flux will not be constant throughout the material.
So yeah, that's right.
But
In the transient case, it may not be constant.
yeah, got it, sir.
In the transient case, it may not
Uh,
be constant.
can we say that, like in the case of the transient state, the resistance that we got here will not be the same for the transient ones?
No, the resistances will be the same, and that is not going to change. But in the transient cases, the temperatures will not be the same, because there would be heat. See, heat could actually get low. So remember this thing, that the in the transient case, you are basically you've suddenly changed the system. You suddenly change some condition in the system. That is what a transient response means, right? So it does not mean that the amount of energy that is going from one into another, it's the same. I mean, if some amount of energy is at some point x, the same may not be going to some x plus, let's say, some x plus c, or some a new coordinate at maybe x1. It will take time for this information to propagate, and that time actually depends on the conductivity of the medium itself. So if the medium is, let's say, very poorly conducting, then the amount of, the response becomes really slow, and so you can imagine it goes very, very slowly. So you cannot have the same temperature, you cannot have the same flux at each location.
So then we can say that electric circuit analogy will not work in transient case.
Yes, in transient, yeah.
Okay, so that is the problem, because the final expression is independent of T and TB,
It
and
is,
if
it is because
resistance
but yeah, but it came out independent to t, because I could write t and tb as constants.
are constant, that's why we could apply the analogy.
Yes, yes.
Okay, so
Okay. So I wanted to do one thing, and I'm running out of time now, but I wanted to do one more case very quickly. But let me just say one thing about this particular system now. If we draw it again, okay, let me draw the slab and the fluid. So we had two fluids, right? And so I'm going to draw the temperature variation now. So let's say this is temperature plotted here, and x is going here. Okay, this is x0 and xl. So remember that I said left side is at a higher temperature. That is just a convenience that I made for myself. So say T infinity 1 is some high temperature and T infinity 2 is some low temperature. And I'm exaggerating the difference just for visual clarity. So what I expect is, inside the solid, we have already seen that the temperature variation will be linear. So this will be TA and this will be TB. That is a linear variation. But what happens outside the solid? What happens on the fluid side? Because remember, the temperature does not change suddenly from, Ta is not equal to T infinity 1. There's a gap, right? That depends on the convective resistance. If the convective resistance was 0, then Ta and T infinity 1 actually become equal. Okay, that's like short circuiting that network, right? So if I say that this resistance is 0, then T infinity 1 and Ta become equal, and that resistance can only be 0 if either the area is infinite, or if the heat transfer coefficient h is infinite. But that's not really the case in actual scenarios and in practical scenarios. So what you will see is the temperature variation, because of the development of a boundary layer, thermal boundary layer. You will see that the temperature goes something like this outside. Okay, that is the temperature variation on the fluid side, and similarly on the other end we can also draw it like that. So that would be the temperature variation in the solid and also the surrounding fluid.
sir, but like we for the convection one also we were considering a particular resistance which was fixed, right? So if we are going from the surface of the body to the medium, then if the resistance is constant and we know that the potential difference is TB minus T infinity 2 or TA minus T infinity 1, then
Hmm.
in that case the current gradient should also be like constant.
No, current gradient. So that has nothing to do with
Oh, sorry,
the.
current. What I'm saying, current. The temperature gradient should be constant.
No, 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 not in the, see, the fluid side, because that is the main difference between solid and a fluid. A solid will actually, because the molecules are closely packed and they're in an ordered system, so they will stay where they are. But in a fluid, you can actually have, there's also bulk flow. Remember, this is not just fluid staying there. It would have been constant had the heat transfer only been because of conduction in the fluid. But it is not because of conduction, it is because of bulk flow.
So, but sir, then how can we consider the fluid, the resistance of a fluid then? If it
Why
is
not? Because see, resistance to conduction, resistance to convection are not the same. Please understand this. Convection, as I said, is because of bulk flow, and bulk flow also has its own limitations. There's an upper limit to convection resistance or convection heat transfer. So this profile is essentially saying that there is a transport across the boundary layer, across the thermal boundary layer, which I had done in, I think, the first lecture when I showed, I think, the concept of the boundary layer. So that's the same part which is dealing with this, that you will have some resistance to diffusion even in the boundary layer.
okay. So basically,
Okay.
the term one by H1 is for the resistance while transferring the heat from the fluid to the body, like at the boundary.
Yeah, in on the left side. On the right side, it becomes from the solid to the fluid.
Okay, sir.
Okay. That is what convection is. I mean, there's a heat. Convection is, as I said, it's a transfer of heat from a solid to the fluid or from the fluid to the solid. Conduction is purely within the same medium. There is no change at that boundary. We don't talk about two different mediums like that, or two different media like that. Okay. So one thing that I wanted to do, and maybe I'll just leave it to for you to figure out, is that if we have, let's say, a composite system, uh, say we have, let's say, not just one, but maybe multiple slabs put in one after the other. Let's say we take three slabs which are put next to each other, and again then we have a surrounding fluid. Okay. And let's say the slabs have some thickness, maybe La, thermal conductivity Ka, Lb, thermal conductivity Kb, and then Lc, and thermal conductivity Kc. And I want you to figure out what would be the heat transfer rate at steady state. So the same concept which I have done, which is the electrical circuit analogy, can still be applied here. So we can do this the same way. Now what we will have is, we will have some potential T infinity 1 here, convective resistance, let's say 1 by H1A, and then we reach, maybe I can define temperatures here just for convenience. Let's say this is T1, then we have T2, T3, T4. So that I know that the solution would actually be a linear profile, piecewise linear, I should say. So it would be linear in every slab, but the slopes can change depending on conductivity. Okay. And of course, outside this, we will have the same thing as I was saying earlier, that the temperature will actually again change in the fluid, but it will reach, after outside the boundary layer, it would reach the temperature of the free stream fluid. So T infinity 1 and T infinity 2. So what we will now have is uh, T1 being here. Then we have a conduction resistance going to T2. So let me say R, or let me write the resistance itself. So we'll have LA by KAA. Then we'll have another conduction resistance, which would be LB by KBA, and then LC by KCA, and then we'll have 1 by H2A, T infinity 2, this will be T3, T4, and some heat current passing through the whole. uh, system of these slabs and the fluids. So we can write again total resistance to be the sum of all resistances, and total current to be heat current to be T infinity 1 minus T infinity 2 by the total resistance, which is again the sum of all resistances because these resistances are in series. So the last thing that I wanted to say is that in these composite systems, it's often convenient to write the overall heat transfer rate Qx in terms of a variable which we call as overall heat transfer coefficient U. So UA delta T. So U is the overall heat transfer coefficient, which has units of watt per meter square, and delta T here is the overall temperature difference. So in our problem, it would be T infinity 1 minus T infinity 2. So it is done very often in this way. And by doing this, what we have now is we can, if you compare, I can easily see that UA would be inverse of the total resistance. And if you simplify, you can actually prove that U will be 1 by H1 plus L by Ka plus, oh sorry, La by Ka, Lb by Kb plus Lc by Kc plus 1 by H2 inverse. So the overall heat transfer coefficient can be easily defined for heat flow in a plane slab, in a plane wall. So we'll use this concept. I just wanted to introduce this today. We'll use this in the next lecture, especially when we talk about heat transfer in using heat exchangers. This concept of overall heat transfer coefficient will come in handy. So I'm just introducing it now. But there's nothing more that I want to say about it at this point. Okay, so anyway, I'll stop it here. In the next class, we'll work out now problems of heat conduction in spherical and cylindrical geometries.